Now today in class 12th I will take a very important topic, that is the suspended coil galvanometer. The question is asked in the board exam and also a complete question may be asked from this topic, that is of 1 mark, or this is of 2 or the 4 marks. So this is very important one. Also the question is asked in the NEET exam depending upon the deflection in the coil of the galvanometer. So as the name suggests that this is the galvanometer in which the coil is suspended in the magnetic field, and when the current is passed through the coil, then it is get deflected, and that deflection gives you the amount of current passing through this one. So this galvanometer is used to measure the current in the circuit, but this cannot be used for measurement of large currents. It measures only the instantaneous currents. Very low instantaneous currents like charging and discharging, like the currents during charging and discharging. Of condenser. Because during the charging and discharging of the condenser, the current is given for a very low time, and this is very instantaneous current and it is of very low magnitude. So principle of now this galvanometer is based on the principle of deflection due to the current passing through it, and when the coil is suspended in the galvanometer, I told you this one. When a current is passed through a coil suspended in uniform magnetic field, the coil is deflected due to torque acting on it. It is called deflecting torque. deflecting torque. And this is given by simple formula that I have told you earlier also, that the torque is equal to NIAB, where N is the number of turns in the coil, I is the current, A is the area of the coil, and B the magnetic field, where N equal to number of turns in coil, I the current passing through the coil, A area of coil, and B the magnetic field. B the magnetic field. So this torque deflects the coil in the magnetic field. So now we have the construction of this suspended coil galvanometer. Construction. Now this is a coil. This is the coil having number of turns this I have taken here. This is a cylinder made of soft iron. This is held suspended. Here we have a strip this is the mirror M. Here we are having this is carried like this. These are the terminals T1 and T2. This is the spring. This is mirror M. This is the strip, and this is now support to this one, and this is now spring. And this we have magnetic poles. S. And this all of the arrangements now here this is phosphor, bronze, white. Phosphor, bronze, white. This is the mirror, that is the concave mirror. Concave mirror. These are the magnetic core pieces, and this is the soft iron core. Here we are having way to tell it. This is now a strip. Strip. This is soft iron. This is the coil. This is coil. So this is the construction of this one. So the parts of this main parts. Number one, coil. Coil having number of turns. Made of conducting wire. Conducting wire. This is now your is coil. Number two, cylinder. Cylinder. This is a soft iron core called soft iron core. Soft iron core. And this is the magnetic core pieces. Concave magnetic core pieces. This is the north and south. M is the mirror. Now fourth is concave mirror. M. This is the concave mirror M. And a spring. This is now a spring. Attached at lower part of coil, and then phosphorus bronze wire. 6 is phosphorus bronze wire. And then we are having this strip that I have told you here. Phosphorus bronze strip attached at upper part of coil. This is now strip here, and this whole arrangement, the phosphor bronze wire phosphor bronze wire and a spring are connected to terminal T1 and T2 as shown in figure. Now here this is not T1 and T2. Now this whole arrangement is made in a airtight glass box. This whole arrangement is made in airtight glass box. The terminal T1 and T2 are just outside to this one, so that they can be connected to measure the current. Now this is now here this the pieces of this magnet, they are of the concave shape, as I have told you here, and these concave shapes and pole pieces give you the radial magnetic field. The concave shaped magnetic pole pieces reduce radial magnetic field. They produce radial magnetic field. So now this is the construction of this the galvanometer, and now I take its working. Working. when the current is allowed to pass through suspended coil, it is deflected due to torque on it. So now deflecting torque this equal to NIAB. Here the theta is always 90 degree due to the radial magnetic field. So this is what the benefit of the radial magnetic field. And this I have told you in the principle that this torque is equal to NIAB, N the number of turns, I the current in the coil, A the area of the coil, and B the magnetic field. The radial magnetic field gives maximum torque, maximum deflecting torque, Now when the coil is deflected, then a torsion couple is produced in the spring that opposes the motion of the coil. As the coil rotates in magnetic field, a torsion couple is produced in the spring which opposes the motion of coil. So this torsion couple is called the torsion couple is called restoring couple. And this torsion couple is given by torsion couple couple. This is equal to C into 5. C into 5. where C equal to constant called torsion constant. And this C is equal to eta pi r raised to power 4 upon 8L. This is now your 2L, where eta equal to called shearing coefficient of modulus of elasticity. R the radius of wire of spring, and L the length. Phi, this is equal to angle of torsion. So this is called the restoring torque. Therefore, the restoring torque, this TR, this is equal to C into phi. So whatever the torsion couple acts, that gives the torsion torque, and this torsion torque opposes to this deflecting torque. So in equilibrium, what we have, that this T equal to torque R, the restoring torque. So this is equal to NIAB equal to C into phi, or this I is equal to C into phi upon, this is now NAB. This is now so much is the current. Now you can see that except this phi, C and AB, these all are the constants. So this C equal, I equal to K into phi, where K equal to C upon NAB, or I is proportional to phi. Thus, the current passing through the coil is directly proportional to the deflection in the coil. Hence, the current through coil is directly proportional to the deflection or angle of torsion. Angle of torsion. So this angle, if we measure this angle, then we can find the value of I. But this phi is not measured like this one. Suppose this is given the spring here and this takes some torsion in this direction, then how much angle is to be taken? This directly cannot be measured. So to measure this angle of deflection, that we use the lamp scale arrangement. The angle phi is measured by lamp scale arrangement. For this purpose we use the mirror that is applied in the suspended phosphor bronze wire. So now this is the scale. This is the scale, and that here we are having this. This is now, and here we will have the lamp here. This is now lamp, and then this is the mirror. This is now concave mirror, and this distance. This is now scale. This is now suppose this is now 0 mark. This is now your 100 mark, and this is now suppose your 10. This is now your 20, then 30, then 40. And then 50, and then 60, and then 70, and then 80, and here this is now 90, and this is now your 100. This is the meter scale. Then here we will have this light. This is the mirror M. Then this distance is fixed from here. That is now D. Now this distance is D. If suppose this mirror is rotated like this, and this angle is suppose now this is now phi. This is now phi. Then the reflected ray here. Then ray will be reflected like this. Then this angle is 2 phi. This is not 2 phi. And let this deflection is equal to D. This deflection is equal to D. This is now right angle triangle. So let this is equal to capital D. So what we have? That this is the lamp scale arrangement. This is now lamp, this is now scale. This is scale. This is scale. The deflection may be on this side also. So this is not reflective light ray. when mirror rotates by an angle phi, the reflected ray from it will rotate by 2 phi. So it means that this angle is 2 phi. So now tan 2 phi. Tan 2 phi. This is equal to d upon d, where d equal to deflection on the scale. Deflection on the scale, and d equal to distance of mirror from scale. So now what we have, since this angle is very small, so we can take it to be now is 2 phi. This is equal to d upon d. So what we have, this phi is equal to d upon 2d. Since this capital D is constant, so this phi is proportional to d. Phi is proportional to d. So this we take, now suppose number 1, and this we take suppose now number 2. Now this is the scale, this is now constant 1. Constant. So this is whole is constant. So from first and second, from equation first and second, what we have, this phi I is proportional to phi, and this is proportional to d. So this we have that this I is directly measured by d, or I is directly proportional to d. So this all measurement gives the value of the current that is passing through the coil. But you see from here that this measurement is a very typical one, and this is also a time consuming. It is, requires a great calculation on this one. Moreover, this angle phi is not a constant one, this different, and this its measurement is also not very easy. So in the board exam, this is asked that so that when the current is passed in the coil of the suspended galvanometer, suspended coil galvanometer, then it is proportional to the deflection produced in the coil. So for that, the answer ends at this point. But if suppose this is given, that also tell it that this is proportional to the distance moved on this scale. Then we have to do this length scale arrangement, and then we have to tell it that this I is proportional to the D. Now we will have some more definitions related to this one. That is now current sensitivity. current sensitivity. So this is given the deflection. Deflection per unit current is called current sensitivity. This is denoted by the term that is to be now different one. Denoted by SI. So this SI is equal to, this is now your phi upon I. Phi upon I. And you have seen that this I is equal to K phi. So this I equal to K phi, and this is equal to C upon NAB into phi. So this phi upon I is equal to SI equal to NAB upon C. This is what the definition according to this one. This is now definition to this one. Now you can have the unit of current sensitivity. So this is now degree per ampere, or we can have radian per ampere. So we can have that this radian is the unitless. This is now ampere is measured in A. So its dimensional formula will be Now this will be your M0, L0, T0, A minus 1. So now this is that you can see that this current sensitivity can be increased. To increase current sensitivity, first this number of turns N, A and B must be large, and second C must be small. So since the number of turns at A and B cannot be increased because this makes the coil to be very heavy, and in that condition the coil cannot be deflected easily. So this N, A and B, this B is the constant, A the area, and N and A, that cannot be increased. That will make the heavy coil. So only the method to increase to this current sensitivity is that C must be reduced. And I told you that C, to reduce the value of C, the phosphor bronze wire is used. To have minimum value of C the spring is made of phosphor bronze wire. This is the reason that why this is made of phosphor bronze. Because for phosphor bronze, the coefficient of the shearing coefficient is to be very small. So because of that, this C will be a small one, and then this SI will increase. Now then we have one more term, that is the voltage sensitivity. Voltage sensitivity. Voltage sensitivity. So this voltage sensitivity, this is just like to this one, the deflection. Per unit voltage. Is called voltage sensitivity. This sensitivity denoted by SV. So what we have? This SV is equal to phi upon V, and this V that we know, voltage V, this is equal to I into RG. RG the resistance of the coil. And I the current that is passing through this coil. So that is we can give to this C into phi into RG upon NAV. This is equal to V. So now we can have, if we have one more formula applying to this V here, this SB is equal to phi upon V. So this is now NAV upon C into RG. This is now like this, where RG equal to resistance of coil, and I the current to reach this one, so that we can have to this, and the unit of this one will be unit, that is now radian per volt. So now its unit will be, if you have the dimensional formula, then you can have that this volt here, we are in W upon Q. So this is your radian upon W upon Q. So this is equal to radian upon, now this Q is equal to I into T. So this W upon I into T, this is not so much, and we can have that this is your m minus 1 L2, and this will be your t minus 3, and t minus 3 is not t4, t plus 3, and this a will be here, t minus 3 is not t, and this a, this is now your a, 1. This is the dimensional formula of this voltage sensitivity. Now we have one more term related with this, that is the figure of merit. Figure of merit. So this figure of merit is given by the current per unit deflection is called figure of merit. So figure of merit, this is generally denoted by the term S, denoted by S. Denoted by S. So this S equal to I upon 5. This is the reciprocal of that current sensitivity. It is reciprocal of current sensitivity. Current sensitivity. So we can have this S equal to 1 upon SI. This is not so much. And now you can have the unit of this one. This is ampere per radian. Ampere per radian. So it's dimensional formula. That it will be your this is only the A, or we can write it to be N0, L0, T0, A1. This is the dimensional formula. So this is what the figure of merit, and all these are the scalar quantities. And we can have the unit of this one. If you note to this I upon 5, then definitely you will find that this S equal to C upon NAB. This is not like this, because this I is equal to C upon NAB into 5. So this I upon 5, this is a C upon NA. So to increase the figure of merit, C must be the large one. But actually our aim is to measure the current by this galvanometer. So for that we must have the large value of current sensitivity. So you have seen that the three definitions, some of them are asked in the board exam, their definitions, their units, and their the dimensional formula. also a complete question of 3 or 4 marks is asked from this suspended coil galvanometer. So thank you very much.